Today we're going to talk about the branch and bound method. This is a well-known and popular method for discrete optimization. It can be kind of a general purpose method, although it's more effective for certain classes of problems. We'll talk about uh, that today. But for general problems, it's not necessarily very efficient. If there's other structure in the problem, there are often better methods. But for certain types of problems, as we'll see, this is a very effective strategy. Um, so at the heart of the method, we'll see one of the things that we do is sort of this bound. We're going to keep track of what a lower bound is, or in other words, the best solution or the best the solution could possibly be. And to know that we actually have the bound means that we have to be able to guarantee that we can solve each subproblem and find the global optimum. And there's only certain types of problems that we can guarantee that we'll find the global optimum. These are called convex problems. We haven't really discussed this, although we have discussed certain types of convex problems. We talked about quadratic programming problems. Those form the heart of the SQP, where, say, for example, if there was equality constraints that reduced even to a linear system. But for inequality, we could also guarantee convergence as long as that quadratic term was positive definite. Perhaps the most popular convex form for these branch and bound problems is a linear problem. So a linear problem looks like this. This is just a general form. We could say, let's minimize some coefficient of vectors times x. So C is just a vector of numbers, right? So these would just be some weights. And so that's a linear objective, right? Because this would be like C1, x1 plus C2, x2 plus C3, x3, and so on. So you can see that's just linear in the variable x. And all our constraints must also be linear. So we could have, for example, ax plus b equals 0, some equality constraints, for example. We could also have, and just to use a different symbol, put a hat here, ax plus b hat is less than or equal to 0 for inequality constraints. So B here is a vector, A is a matrix. So each row of this is just a linear constraint, right? It would be something like, say, A11x1 plus A12x2 plus A13x3 plus ... plus B1 equals 0, for example. And we can see there's just another linear equation. And now we put it in matrix form because there's a bunch of them. Okay, so this here, we call it an LP, or a linear programming problem. This is convex, meaning we are guaranteed to be able to find the global optimum. We can solve these very efficiently. And they're very popular in, say, operations research, like transportation problems, networking problems, all sorts of cases like this. We did an in-class exercise, just to recap, one example where you actually did this in Excel, and that is using a branch and bound method. Often when you solve these linear problems with discrete variables, they'll use a branch and bound method. But in that example, say this was like C was cost, right? We're trying to minimize some cost. And so these were the products we were making, and we were making some integer number of them. We were just summing up the costs, and these linear constraints would be things like resources. Each widget I make takes a certain amount of resources, and I can't exceed some specified number of resources. So those are often linear constraints. I want to figure out like the right mix of products to manufacture. So these kind of problems occur a lot, like in sort of that manufacturing sense, or in a transportation sense, where maybe I want to minimize the distance or the cost of transportation. We talked about kind of this traveling salesman-like problem, or say I wanted to do this airport problem, right, where I was trying to go from airport to airport, find a minimum cost. Maybe I have various constraints on my shipping that I can pose in a linear form. Maybe there's some different weights or things that I can carry, and I can't exceed a certain capacity. So these occur quite frequently in what is called operations research. We can use them for other problems, but I'll kind of recap that at the end. They just in general are less effective, because one of the things that we're going to rely on is that we can solve the subproblem or in other words, a subproblem is going to be this problem where we ignore for the moment the discrete part of it. We need to make sure that we can guarantee a solution and then that it's a global optimum, and that's just not possible for general problems, but we can here for these linear programming problems. So this isn't really our complete problem. That in itself was the LP, but then we're going to add this additional constraint, and I'm just going to, I guess I can write it this way. This is the mathematic notation here. For all or sum of I. This just means this is a set of integers, and the positive means it's a positive integer. So this means that all of my x's must be integers. This is that integer constraint. And here we're restricting to be positive integers. That's the most common case here, right? Where we're talking about how many goods to produce, or you know, what nodes to connect or whatever. It doesn't make sense to produce a negative amount of some good generally. Although it could. In that case, we could just, without any loss of generality, just put a negative weight here. So this is actually completely general. So I guess you can ignore what I said about negatives. That's totally acceptable here. Yeah, and just to be clear, that negative is captured here in the weight, not here. So this is general, that we assume that these x's are positive. Okay, so these are positive integers. And so without this, it's an easy problem, it's an LP. But now that we've added this constraint that some of these variables are discrete, they're integers, then it becomes a bit harder, and we would call this, say for most commonly, a mixed integer linear programming problem. So this is a MILP, mixed integer. Mixed meaning there's potentially some integer, some continuous variables. Okay, so before we jump into the algorithm, one step that's very helpful is to convert to binary, if possible. So we just said the general problem is that these x's, these design variables could be integer variables like 1, 2, 3, 4, 5, but it is much easier to solve usually the branch and bound problems if our variables are binary, 0 or 1. It is often, though not always, it's often possible to convert an integer problem into an equivalent binary problem. Sometimes we have to add maybe additional variables or constraints or whatever, but we can often do that conversion. So here's an example that you can think of. So let's say we talked about some examples of integer problems. Actually, we mentioned this as discrete. Like I wanted to choose the material for my car. You know, should I make this out of titanium, aluminum, steel, or whatever, different alloys of steel? I could have a bunch of them. So here's let's say this is my original problem. I've got one design variable, and this is, I'll give it a y, so it's different from the x's. And y can be 1, 2, all the way up to n. And these are represent n different materials. Okay, so that would be the way we could specify the problem, right? We just map each material to a number. 1 is steel, 2 is aluminum, and so on. And the optimizer needs to choose that design variable. That fits this form fine. But to be more efficient, we would like it to be a binary problem. So you might pause at this moment, pause the video and try that, see if you can convert it to a binary problem. So here's something we could do to convert, right? So let's do some conversion here. We could say, well, let's make more design variables. Instead of having one design variable, we're gonna have n design variables, okay? And each of these variables, we want them to be binary, so it's either 0 or 1. And so 0 means don't select that material. Boy, I'm having a hard time writing. Don't select. And 1 means we do select. So now I have n design variables, not 1, but n, 1 for every material. And so it's either gonna be a 0 or a 1. I either select that material or don't. Obviously, that's not good enough because I need to select just one material at the end. So we're also going to add a constraint. What kind of constraint could I add? Well, I just need the sum of these to be equal to 1, right? Because I need everything to be 0 except for one material, the one that I choose. So I add the constraint that the sum of these is equal to 1, and that's a linear constraint. So this, all that's saying is that We only can select one material. So we're able to successfully convert this problem, this integer problem, into a binary problem. All my decision variables are now zeros or ones. There are more of them, and I added a constraint, so it seems like it's harder, but it's actually much easier usually if we do this. Even though it's a bigger problem, it still ends up being easier to solve. Okay, so we'll now go with the assumption that we've done that. Let's just look at an example here, one that we're going to look throughout today. Here's just an example linear problem. Notice it has those binary constraints. So here's the objective. You can see it's a linear function in X. And these are all linear constraints. There's two constraints. And then we have this binary constraint, every X. And here we don't have any continuous variables, although we could in general. But each one of them has to be a 0 or 1. Okay. So the key to solving these kind of problems, or any branch and bound problem, is we use what's called a relaxation. And a relaxation means we're going to solve an approximate problem, where we're going to generally relax some of the constraints, meaning we're going to remove some of the constraints. So the first way we're going to do this, and this is how we'll do it throughout, this is the natural way for at least these integer problems. For other more general problems, there might be other relaxations that could be better. But in this case, an easy relaxation is just to say, let's get rid of this. All right, let's get rid of that constraint. Then it's an easy problem to solve. Every optimization package has linear programming solvers. It's convex, right? So it's guaranteed to solve, global optimum, very efficient, very fast. It's an easy problem to solve. So that's great. We can solve this problem. So, and let's say, just by chance, when we solve this, we happen to get all zeros and ones for the answers for X. Well, then we'd be done, right? We solved the problem because we let it do whatever and it gave us zeros and ones. So we know that's actually is the solution to our original problem. But that's unlikely to happen, right? So we have to keep moving forward. However, what it does tell us, when we solve the problem, it's not a solution to the problem, but every time we relax it, we know that we couldn't do better than that. That's a lower bound. It's not a lower bound to the solution yet, but it's a lower bound, meaning that's the best we could possibly do, because if we add these constraints back in, if I erase this, it could give me the same answer. If it did, I would have been done already. But in general, adding more constraints means I'm going to get a worse solution, right? Worse in the sense of the objective, not worse in the sense of our goal, but a bigger objective when I'm trying to minimize. So I know that that relaxed problem is a lower bound. I can't do better than that. Okay, so that's going to be an important point that we will use. Here's maybe a visualization of a start on the idea of the branching portion of this. So the branching portion is this first node here is this problem where we got rid of this. So ignore that for the moment. If we ignore that for the moment and we try and solve it and it didn't solve, so now we're going to branch. We're going to try two different options. Because X1 only has, let's say we branch on X1 first. X1 only has two options, really. It's only a 0 or 1. And in fact, this problem is small enough, right, that we could try all the combinations, but of course, that is not scalable as we've seen. But now I'm going to solve a new problem here where I choose X1 is 0 in this branch. So this node here says, let's go back to this problem here. Let's solve it, but we'll just keep X1 0. We won't optimize X1. We'll fix it at 0, solve for the other variables. Okay. And we could keep going, right? We could go down further and we could say, okay, now let's keep X1 0 and X2 0 and try to solve for the other variables. And maybe it gives me a solution, maybe it doesn't. And I could keep going through all of these. And you'll notice, right, if I did all of these branches, I would have done exhaustive search. In other words, I tried every combination, and that's not good, right? Because that kind of defeats the whole purpose of having an algorithm. But what we'll see is that we can eliminate branches. What's going to happen is that we may meet some criteria, say here, that says we know nothing below here can be a solution, so we can just get rid of this whole thing and not evaluate it. Or maybe we get here and we realize, okay, we can't go any further here, and we can get rid of all of this. This is called pruning, when we cut off some of these branches. Okay, so we've kind of had two keywords here so far: the branch part, and we've mentioned briefly the bound part. This is a lower bound. we're going to kind of put these together now. So let's see how we could prune. Here's the diagram, and this is really the key to this, is that branching through every possibility is exhaustive search. But if we can prune, we can cut off branches, we can severely restrict the number of combinations we have to find and still guarantee that we can find the optimum, right? If we have a linear problem, this is one of the cases where we can find the solution, right? Even though we didn't try every combination. We're taking advantage of that convex structure. All right, so here are some possible outcomes. Let's say I solve this problem, that problem where I relax the problem, right? So in other words, I got rid of the integer constraints, and that's going to repeat throughout, right? So I'm going to go through here, and let's say I fixed x1 to be 0. I still eliminate those integer constraints, and I try to solve it again. And let's say when I try to solve it, it's infeasible. If that problem is infeasible, what does that say about the rest of that branch? If I went down further, what it says is that that entire branch is infeasible. So we can prune it, because if I go down further in that tree, remember, all we're doing is we're adding more constraints. So we're saying first, just fix x1 to be 0. Now fix x2 to be 0, right? Don't let it have any more, don't let it vary to whatever. So if the problem could not be solved before, fixing one of those variables and not letting it move is not going to let it be solved any easier. Right now, it's still infeasible. So once I find any solution that's infeasible, so let's say this one here is infeasible, that means all of these are also infeasible, and so I don't have to evaluate them. Right. So in other words, the general principle is if I can solve a problem, like and really for this to work, I have to guarantee that I have actually know that it's infeasible, and this works in this case convex. If I know for sure it's infeasible, then adding more constraints can never change that, right? That won't ever make it any more feasible. Okay, so we could prune, that's great. So another is that, let's say the objective is worse than our best solution. If the objective is worse than the best solution, then what does it say about points that are further down on the branch? Remember, every time we go down the branch, we're adding more and more constraints. Well, if we add more constraints, and again, this is true if we can make sure we're getting the global optimum, adding more constraints will never improve the objective. It may not make it worse, but it can't make it better. So we know that if we found a solution that's already not better than the best we found, then nothing from that point on will be better. So we could prune that as well. So let's say we got to this point here and we say, oh, we have a solution, and here, this isn't a solution even. It may not even be a solution. It's the relaxed problem. But we know it's already not better than the best. So adding more constraints, even if there are solutions down there, we know that they're worse than the best we've found. So we can get rid of all of these and not evaluate that branch. So if the objective is worse than the best solution, we can prune. And I guess the obvious implication there is that we do need to keep track of what our best solution is so we can compare. Okay, so those are the two pruning parts. The two other possibilities is that we find a solution. Okay, so maybe we find a solution, and that means, we get to some point here. Let's say I get to here, and even though I didn't constrain everything, I constrained x1 and x2, and x3 and x4 and whatever other variables happen to give me integers. Then that's a solution, right? I satisfied that constraint of the binary zeros and ones, so that's done. The problem's not done because there may be many solutions here, right? And I have to find the best, but that means I can prune, right? In other words, I save that solution, I compare it to the best, but there's no need going further, right? Because again, adding more constraints can't improve it. So even if there were, and there really can't be, but if there are other solutions on that branch, they can't be better. So that's it, right? So there's a lot of things I can do to prune here. Otherwise, we have to keep going. That's really the fourth possibility, is that we don't have a solution, but it still looks promising. It could be better than the best. It's still feasible, so we have to keep branching and go further down in that tree. All right. So again, this is the point, and I'll come back to this again. These kind of points, especially these two, actually really even the third, is what hinges on the fact that we can find the global optimum for this relaxed problem. This is why we need something like an LP, a linear programming problem, or other convex problems, because those we can guarantee it. If it's a general problem, and we're pruning because we say, well, it can't get any better, that might be because it can't get better. It might be just because we found a local optimum and we pruned too early. So we're not necessarily going to find the best solution. It's and each of these subproblems becomes more complicated, right? Because we have to solve a sequence of them. So anyway, we'll get back to that later. This is the method. Let's kind of go through an example now. Well, actually, before an example, I'm going to talk about a few sort of design choices here on the method. So one question is, which variable to branch on? So in the above figures, I just branched on x1 first and then x2 just for a picture. But let's say I solve a problem and there's only 4 variables, and this is my relaxed problem. I get, just make something up here. Let's say I got 1, 0.2, 0.6, 0, 0.1, or whatever, okay? 2 of these are already integers, so I don't need to branch on them. They might change later, right? They're still free to change. But these ones I should branch on because they're fractional. So I'm going to take a branch. I could do any one of these, but a common choice is to branch on the one that is closest to 0.5, meaning it's not close to 0 or 1. The logic there is that these ones that are maybe closer to 0 or closer to 1, we would say, well, they're maybe getting there, right? They probably could nudge that way more easily. And here we're forcing a decision faster. We're saying, okay, let's just force it, try it with a 0, try it with a 1, and resolve it. So it tends to be more efficient if we use that component that's biggest fractional component, meaning it's closest to 0.5. Another design choice is, should we do a depth first or a breadth first? Okay, that means when we branch, should I continue down this branch all the way to the bottom until I can't go any further and then work my way up? Or should I go here and then here and then here and then here and here and here and back up as I need, of course, but what's the strategy? And most commonly, depth first is usually desirable. And the reason is that by forcing more and more and more constraints, we usually force a solution faster. And that's helpful because once we have a solution, we can compare it to others, and that helps us prune faster, usually. It also means we don't need as much of a history, because when we're doing depth first, we just only have to keep track based on the number of nodes. But if we do breadth first, we have to, the amount of things that we have to keep track of and to keep in memory to compare grows as we get further and further down. Anyway, so most commonly depth first, although in the examples today, I'll actually show breadth first just because it's easier to show with these small examples. And actually, I think in the one case it went faster, so I just we'll do that today. All right, so here's that same problem we were looking at. So let's step through an example here and work it. I actually won't solve all the subproblems, but you can do that. This example is in the book. I'm just going to show you kind of the steps. So what was the first step again? First step was to relax the problem. And I guess I was maybe being not specific enough. I said we're going to eliminate these constraints, which is true, but we're not going to just eliminate them. We're going to replace them with bound constraints. So we're going to say we're making it a continuous problem, but we are going to say that they should stay between 0 and 1. Right? It makes no sense for us to just allow it to be whatever, right? It could give us 2, 50, whatever, because we know at the end it either has to be a 0 or 1. So let's keep it within those bounds at least. It's still a continuous problem. It's still a linear constraint, easy to solve. It's even a bound constraint. So we can solve this still really easily. So let's say we do that. Okay, we solve it. And here's what we get. Here's the solution to that linear problem. And again, you could plug this into any linear programming solver. So, it'll be easy for the optimizer to deal with this. And so we get 1, 0.5. I'm just going to write 2 decimal places here for brevity. 0.53, 0. In 2 decimal places, it's 50, 1. Okay, so those are my variables. And the optimal F, just for interest here, is minus 5.03, just with 2 decimal places. So this is not a solution, right? Because I have 2 that are binary, but these 2 are not. So I have to branch. I'm going to branch on the one that's closest to 0.5, which is this one on x3. Okay, so what does that mean? So here's that first solution we saw. I'm branching on x3. So I'm going to solve this same problem, except for I'm going to now take x3 out of it. I'm going to say in this step, let's just say x3 equals 0. So it's not a design variable anymore. And now I can let x1, x2, and x4 vary freely, right? Still within these bounds, but they can vary freely. Okay, and that's going to be this node. The other node is same problem, but force x3 to be 1. So x3 is forced to be 1, and then we let the others go freely. Okay, so here's what happens. Here, right, x3 was forced to be 0, and we let the other 3 vary freely. And in this case, it's still not a solution. So we're gonna have to continue. And let's try this side. Right, normally I said we do depth first, but for this picture, it's actually easier for me to show you breadth first. So here, let's do this breadth one. And here we solved the problem. Remember, we fixed x3 to be 1. We let the others vary. Notice, right, all the others are free to vary. So even though x4 was 1 before, it's not 1 now. We didn't force it to be 1, right? We're letting it be whatever it wants to be. And this is also not a solution, so we have to keep going. Okay, notice that there's another thing, notice each time we go down, right, this constraint, or sorry, this objective, this is our lowest bound. This is the best that could possibly occur. Now we know it's not a solution, so the real solution is gonna have a higher objective. So as I go down and I've added more constraints, notice that each of these is worse. They could be the same, but they can't be better. Okay, so now I know I can't do better than that, at least on this branch here. So let's keep going. Here, actually, this was pretty close, right? 1, 0, 1. So the only one I could branch on is this x2. So let's branch on that. Okay, so here we are. I branched on x2, and so now I still force x3 is forced to be 0, and x2 is forced to be 0, and I let 1 and 4 go free. I let them be whatever within the bounds 0 and 1, and they both hit the bounds. That was the best solution I could find with those constraints. So this is a solution. That's great. So we're going to keep track of that. We're now saying this is the best solution we've found. So it's something we're going to compare to. F star is -4. It doesn't mean there aren't other solutions. We don't know that we've actually solved it. We just know that any number that is already bigger than that, well, we know that this is a lower bound. We can't, anything that's a solution, or sorry, any value that's higher than that is not going to be useful. Okay, so let's keep going. Just going to say something on that. I don't know, I'm not sure I said that right. Let me get back to that in a sec here. So let's do this next. I'll recap that here at the end. So let me just finish the rest of this row here. Okay, so I solved the next one because again, I still have this branch. I wasn't able to prune it yet. Here it is, right? So we fixed x3 at 0, we fixed x2 at 1, let the other 2 vary. We get a solution. It's not a solution, right? Because this is still not binary. So we would in general have to continue. Here, this one gave us a solution. This is all binary values. So this is a solution. And this is now our new best. -4.9 is the best. And then this one is not a solution. But here's the thing that we notice is that now we have updated our best. It's -4.9. So anything that is worse than that, yeah, I know what I misspoke on. Let me correct that in a second. Anything that is worse than that, yeah, sorry, I'm thinking of 2 things at once. Okay, so anyway, this is a solution. So this means that this value here, we know as we go further, we're adding more constraints. So this objective cannot improve further, right? Anything that's below here is going to be bigger than -4.49. But we already know that we have a solution that's -4.9, so there is no need to continue this branch any further, right? Anything below there is either going to be -4.49 or worse, right? Bigger. Same with this branch here, right? We got -4.52. So there's nothing, you know, if we keep going, we could branch further, but we know even if there's a solution there, it's not going to be better than this one, right? Because minus 4.52 is already worse. Yeah. So, okay, yeah, I did speak correctly, right? So the idea here is that this was minus 4. Let's say that this value here was minus 3. It was already a worse solution. We wouldn't even have had to evaluate those. But because it's minus 5, it's not a solution, but we know that there might be a solution that's still really good, right? Because this is giving us minus 5. But as we come down, and now we got a new value, minus 4.9, anything that's bigger than that, which is this and this, we can prune. So now we're done. We've pruned every branch. There's nowhere else to go. So this is the answer. This is the optimum, the only solution to this, or yeah, not the only solution, I guess the solution. This is the global optimum to our discrete problem. And we're able to do that again because of this linear structure that we're taking advantage of, that we know we can solve those subproblems globally. Okay, so again, an important point to note here is that even though there was a solution, we're not done. We have to make sure we've exhausted each or pruned every branch. And again, this is not an exhaustive search here because we only went 2 levels, X3 and X2. There could have been 2 more. And of course, in general, there could be lots, right, depending on the variables. So that was breadth first. I'm not going to walk through it entirely, but I just want to show you what it looks like with depth first in this case. So here, the depth first was just always to go left first. So we branched on X3 like before. That was not a solution, so we branched again. We found this solution exactly like we did before. So then we come back up, we come here, it's not a solution, so we branch. We found a new solution, but it's worse. It's worse than this one, right? So keep going, branched, another solution, it's still not as good. We branch, and then this is infeasible. We've now constrained everything, and it's actually not a solution. So we back all the way up, come down, and here we get a solution. This is our new best, minus 4.9. So we save it, and then we come here, and it's bounded, just like it is here, right? It gives us minus 4.49. So we know, well, that's worse than the best we've found so far. So there's no need to continue. In this case, the breadth first happened to be faster just because the solution was here. But in general, depth first is usually a preferred strategy. Okay, so what if you couldn't use binary? We talked about this whole thing with binary. And as we said, you can often convert integer problems to binary. But if you couldn't, another thing you can do is you could do the same kind of idea. So let's say we're required to have integers, right? Let's say, you know, I've got 1, 3, 6.2, 7. Let's say these are my variables, and I now want to branch on this one. I can't make it 0 and 1, but I could do this. I could say, let's do one branch where x3 has to be less than or equal to 6, and then the other where x3 has to be greater than or equal to 7. So we're trying to put those integers on those bounds. And because it wanted to be in between those two, it's likely that it's going to hit one of those bounds. Not necessarily, though. This tends to, well, this is in general not as efficient. I'll just show you as a picture. I'm not going to walk through in real detail, but this is in the book. Here's another problem, another linear problem you can see. And here, this one is mixed. So the first 3 variables, 1, 2, and 3, have to be integers, not binary, just any integer. And x4 is continuous, just any continuous variable, you know, positive variable. So here's what this looks like. So we branched, for example, on x3, and based on what its value was, we said it had to be less than or equal to 4, or greater than or equal to 5, and then we keep doing that. You'll see, though, that one of the problems of this method is that in the binary case, as you branch, you would never visit a variable more than once, because every variable only has one possibility, or 2 possibilities, right? It's either 0 or 1. So once we branched on x3, you would never see x3 appear again in another branch. But here it does, right? So x3 is less than or equal to 4, but then we also see, well, maybe x3 is less than or equal to 2. We're tightening those constraints. x3 is greater than or equal to 3, right? So just because we added one constraint, we may have to add other constraints to kind of tighten that window. And so these branches can become quite a bit longer sometimes, whereas they're bounded for the binary case. So that's one reason why the binary is advantageous. Okay, so as a final point here, just to recap, we did everything in the context of linear, or really convex problems in general. But you can do this for a general problem, and there are branch and bound methods for that. we basically use a similar type of idea where we use these kind of constraints. We'll take these continuous constraints and try to branch on constraints. The problem in that case is that this is not a guaranteed method. It's just a heuristic that we hope it will work well. But because we're not guaranteed to find the global optimum each step, a lot of those pruning steps can be overly optimistic and not give us a good solution. The sub problems, because we solve a whole bunch of problems, if they're not convex and easily solvable, that can become expensive, especially because these trees can be large for large numbers of variables. So if you don't have a linear problem, it's usually only practical with a smaller number of variables. Otherwise, the tree gets too complicated. But anyway, that's branch and bound. This is, like I said, this is a popular method. So if you are solving a mixed integer linear program, it's likely that the algorithm you're using is a branch and bound. It's, like I said, particularly effective for these linear problems or other convex problems. Okay, so next time we'll continue our discussion with discrete optimization, and we'll see you then.